Ladies and gentlemen, welcome to Turn Right Machine Works. My name is Keith, and this is part 2, Set Your Standards and Never Settle, part 2. Alright, just saying, I did leave you hanging. I didn't intend on leaving you hanging. In fact, that video, I had the hunch that this slug, and I still have the slug here itself, and everybody in the comments, I love the comments, and that led me to come back out here. And before we continue on the video, I never had any after the fact video on this slug coming out of the propeller. Okay, the key is right here. The key, when I popped that taper out, fell down on the floor underneath the wheel, and I never grabbed it, never brought it up. Okay, and I'm going to bring you in close so you can actually see this key, and we're going to go back to the picture of actually showing this in the slug, and the same sea worm shell is still on the end of the key, and it actually fit in there right there. So by the photographs, I have proven that this key was in here and in this direction right here, and we're going to take a look at it. This brake, like every other brake I've seen on a shaft, with the exception of 1 or 2 that was over horsepower, created this brake over a period of time. And that wheel was not on the shaft tight. That by no means was a tight fit for a propeller. I should have never been able to get it out without putting a press to it or a puller on it, and then giving it either heat or a severe hit to pop it loose. Alright, so let me bring you in a little closer, and let's get into deciphering all the marks and all the information that's right on this piece right here that tells you the fit, how loose it was, and why it broke. The first close-up I'm going to give you here is of the key, and of course you see part of the slice here of the break of the shaft here, but this is the sea worm that's still left on here, and that is the same position that is in the photograph of it still in when I had it in it before I removed it from the propeller. Here's a picture of that. Okay, now I'm going to grab a hold of the key, and I'm just going to go ahead and I'm going to rock it with the free play. Okay, this, I haven't done nothing to the keyway. This is still all virgin from since I've taken it apart, and the keyway is virgin as well. This is how loose that fit in the shaft itself. Okay, now I'm going to pop this out and I'm going to lay it on its side, and you can see the split line there. Let me bring you out a little bit here. Okay, you can see the split line where the key and the propeller were mating. There's that side, and here's the other side. So we were looking at that split line where they meet. Okay, I'm going to see if I can lay this like this. Let's see if we can zoom you in, see if I can get that straight enough line here. I'm going to see if I can get this angle in here, angle of the dangle here. Okay, it looks like. Okay, now I'm going to lay a scale on here, and then I'm going to put a light behind here. That ought to give you at least, let me see, I'm holding as flat as I possibly can there. We'll go for another position here, a couple positions. But you get the picture, it's almost like an hourglass in there. Okay, we flip the key over, we'll see if it shows any better on this side here. Okay, so this fit on the key, the rocking action, and the sign of it being slammed back and forth, back and forth, back and forth. Yeah, I know it gets old, but and that's what the Aquamet material says. This is getting old, and then it ends up breaking, and it breaks. This key travels up and down in here, and that's the other shaft. You saw the die check from the mating shaft, which had the same kind of fit on it. It was cracked in a couple different areas, so the key probably drifted forward and aft on in the key slot and created a couple different breaks in it. And here's a refresher picture of that. Now let's go ahead and look at the break-in itself. And there's two things here that tell me that it's broke over a period of time. And one is multiple colors of the face. Older breaks will be darker because water has sitting stagnant in the crack and created a coloration, because it's starting to affect that area. And the clean and fresh break is where it hasn't had enough time to actually sit. And also the next thing is you have waves in here, meaning it broke in multiple applications. Every time that key would slam, it would tend to move that crack just a little farther, a little farther, a little farther. And each of those impacts might be a little bit different hardness or torsional impact difference. And then it worked its way on around until it finally had no area left except for to break off. And actually it was kind of hanging on the slug sideways here and here. The captain said he felt he was just backing out from the dock into the channel and maneuvering just a little bit, and something felt funny, and that's what it was. This was barely hanging on, so that prop was doing everything but going straight. And finally he had zero thrust, and he dropped the wheel in the channel right by the marina. Here's the last surface that I'm going to look at that actually tells me that this propeller rocked back and forth on the taper as much as the keyway would allow that propeller to rock back and forth. Normally when you see contact, you can hardly, you see like a water line here, and you see a void down in here. Those are typical contact areas that you see on shafting. But these little gray marks that run back and forth like this, they are like fret marks, okay? And the fretting of the bronze and the stainless, that minute amount of shifting back and forth rubbed that material, and those are all fret marks that are caused by rotational contact, meaning slipping, like slipping a clutch, okay? Just like frying your clutch plate. That's the mark right there that shows movement. Okay, I'm going to give you a couple examples here of driving items with tapers. And all of us in the machine shop deal with Morris taper, slam it into the tailstock, slam it into the quill of the drill press, and you're asking this taper. Not every one of these machines has a tang, but the tang actually serves for two purposes. Basically popping it out and locating it and locking it in there, and it's basically a safety. But if the taper's not holding that, especially in a drill press, that drill chuck is going to fall out. All right. We also have tapers like the number 40 taper, 30 taper, 50 taper as well, all different sizes, different size machines. They do have a drawbar that pulls it in, but you have to whack it to break it loose still. That taper is locking, okay? This is the same principle with marine shafting. Propellers and some couplings are fit with 3/4 inch per foot taper. That's the standard, except for metric shafting. But the same principle, and the taper is what actually holds the two items together, creating the grab that's going to drive that item. Okay, when I pop this out, that key just fell out and laid on the floor. Just as simple as that. I haven't done nothing to that. I haven't done nothing to this. Okay, I just didn't pull it back up there. So you guys are going, hey, there's no key in that. Okay, and there was. It was down underneath there. That key, those nuts, and that cotter pin are safety factors, safety devices that are incorporated into a propeller end, and couplings are held on by other means. In fact, you'll see the means that the couplings, because the shafts we're working on in this video are double tapers, okay? And you'll see me and what it takes to go ahead and duplicate the method of holding on the coupling. When you become complacent or simple-minded, thinking that that key, those nuts, and that cotter pin are what holds your wheel on, you've already lost your battle, and you eventually will have this happen to you. All right. So anyway, what you do to create a better fit than this was put together with is a combination of two teams, the machine shop team and the marina or the assembler. It's team effort, okay? It's not all the machine shop and it's not all the assembler. It's a combination of the two. And to follow through that whole process from beginning to end, that's the whole deal. That's the package deal that gives you the best insurance. There's nothing that says absolutely. Everything is like 99.9 if you've done everything to the T, the best you can. Because even this shaft right here had radius keyways. It had a spooned out key. It had everything put into it. The machinist on the shaft, the only thing I could call him out on is this leading edge was sharp right here, and that kind of will peel brass if it slides through and the mechanic doesn't quite get it on right. It's the only fault that I could see on this end here. Okay, but it wasn't ever lapped. Okay, and it also was never put on tight. And it's the mechanic at the final end that does the assembling and knows how those two parts go together. All right, so you're going to see in the videos here, I'm going to be doing all that should be done to a shaft before it goes out the door to be assembled. All right, so in the comments there, you guys wanted me to tag you on this shaft here itself and why it was fit there. And those of you that pull wheels and everything else know that as soon as that thing popped out of there with the second hit with my 3-pound maul, that it never was put on tight. Also, the reason why I actually set up the camera to do that is I got word from the marina that the other side came off a quarter turn past hand tight, and that's all that was. So I kind of knew that if one shaft was like that, I found cracks on it, and also I have a shaft that's actually cracked off. I pretty much know that the fit on that wheel was never properly done. Okay, you could actually have a shaft that wasn't put on right, run for a little while, the prop was probably pulled off and sent to the shop, but it already had a crack developed, and somebody worked the shaft or didn't work the shaft and just brought the wheel back and put it on there. And it could be put on right the second time, but the crack was already started in there, and that could actually continue on as well. So pinpointing exactly when that crack started, it's hard to tell. The coloration actually tells you. Sometimes they're more than that. Actually, I have another one here, and this was for a Seaway, and that wasn't the reason why it broke. Seaway just happened to be the boat it was on, and it you know, the same kind of thing, and the piss poor contact area here, no lap fit. Okay, and this actually dug in and damaged the wheel in there because it was the way it was sitting there. All right, let's get back to our movie. We're starting another setup that we can do, and it has been planned, and we've had other things in the past run out, hang off our outside crane, and come in with our 90-degree head on the K&T and put a hole pattern on the end of the shaft, and that's what we actually have here. We have our marine shaft sitting out there on a pair of sawhorses, and we'll grab them one at a time, and we'll be bringing them in multiple times to do the hole pattern that we're planning on putting on. Here's a picture of the end of the shaft of the sample that we got to play with. Alright, now this flange here bolts onto that hole pattern there, and this plate actually sets the coupling slides on the end of the shaft. The plate goes up here, those 3 hole patterns go in there, and that helps tighten and secure this coupling onto the shaft instead of having a nut to draw it on. I'm going to need that over here. So what we've done is we've taken a sample piece of shafting, the same exact diameter as our shaft. We put a real small center drill hole in the end of it. Then we brought in our coaxial indicator here, and we've indicated that hole dead nuts. Now I have a spacer setup that I've had for a long time because I use along with this vise, even if I'm in here and I'm hanging off the other end with just a straight shaft and I'm going to put a keyway or whatever. This spacer actually will set over here, and with that spacer and how I feel putting that spacer in will be gauging my height and load out here. Now what we're going to do is we're going to back out of here, and then we'll raise the table up to come from center to center of our hole, straight down in line. And then we're going to go ahead and we're going to put in one bolt hole, drill, tap it, and then we'll put a bolt in there at the end of the shaft, and we will take depth mic or our dial calipers, and we will set this plate exactly round and equal side to side in relationship to the one hole we put in here. And then we're going to transfer punch the other 2 holes, and then we'll rotate the shaft after that single hole to pick up the other 2 holes, and then that'll secure this. After we do that, then we'll move on to doing the keyways, and we're going to do the keyways the same way as we're going to bring them in through the opening of the door out there, and we're going to let the shafts hang out there. Normally I run everything the other direction, and they bypass the my office desk, and I move the table and I kind of hang them with my overhead crane in here because it can straddle the mill this way. But these are a little bit past the length of comfort on snaking everything into this direction, so why not just run off here? The mill's designed to work both the ways. We just run our cutter in the other way. Alright, so let me go ahead. We're going to back out of here. Pretty easy. The offset of this hole to center is 5/8 of an inch, so it's just 5 cranks of the handle, because that's what that handle reads. We always put in our tap follower, and we want to physically measure that. All right, and we're right on the money. Okay, we're ready to bring our shaft in. Bringing a shaft into the shop here is a 2-step process. We got to bring it in, and we have a block here and a block in there, and we set it on down because what we're going to be doing is it's a little bit past center for this to hang into the mill there, but it's not extremely past. It's only like 22 inches past center. So what I do is I pick it, and then we slide it in, and we lift it up, and then I hand lift that up into there. So okay, now before we do this, I go ahead and I set my beam up on the resting spot so it's solid. It doesn't have any bounce or sag to it where it normally does out here, but it's also nice and rigid, and it holds a better height there. We got our beam slid over into place, locked it up in position, so the beam is solid. So it's a rigid hold, straight up and down. It won't change, it won't fluctuate. There's enough distance out here, and there's enough variance, or there's enough span between there and here, that the little bit of in and out travel is not going to matter on steering it. The table and everything else will hold rigid enough, and this will flex and move around as far as the amount or minute amount of raise and lower that you actually do swinging in and out. Once I get this up in here, I'm going to show you how I leveled this out with my special block I put in there. Okay, we want to slide this back 20 inches, 22 inches. Happens to be right about there. All right, move a few things out of the way here. Okay, we're holding on to all the straight that we can before the taper. So we let the taper hang on out here into the air. All right, now it's held rigid by this, and we eyeball our straight. As far as in line with the vise. Now we need to have the right pitch. We could put a level on here and everything else, but this fits exactly underneath on top of the table here. And right now I have about 1/8 of an inch of gap. So what I do is I back off just slightly on here. I want it to hold the shaft true, but I want it to pivot in there, and its own weight is actually going to keep holding it down to the bottom. And I grab the bottom, or the downward pole, and I get the feel exactly right there. And we kind of always go a click or two, making sure that we're on the load on the lock of the ratchet on that hoist up there. Okay, we loosen, we just make sure that, see, that's how tight that fits in there. All right, and slip this back in here. All right, now we can go ahead and we can lock this down where we're firm. We know we're not going to flux, move around. Okay, I just put a small center drill in here. Not that we're going to center drill a hole. I'm just going to get the point started in here. we'll back it out. Okay, I'm gonna run. This is like a. Let's see, what did I pick? I picked a 1964 drill bit. Is what I picked for a pilot drill. Okay, and I'm going to go ahead and take my scale here. We measure out, and we're going to wipe off these 2 lines here. All right, I'm just keeping track of my depth here. I want to go about 1.5 inches or 1 5/8 in, and we're gonna put a line right there with our Sharpie. They rub off, and so there's one line here. You know, I use it a lot, but I use that straight line as my reference. And this is eyeball. Just I want 1.5 inches in here so we can carry at least about 1 inch, 1.25 inches of threads. I'm going to go ahead and auto feed this. This is a fairly new drill bit. It does have a nice cutting edge on it. Aquamet is tough to drill. You need to have constant pressure, and keeping it lubed up with the cutting oil really works pretty good. Got about another inch to go. Okay, there's our 1.5 inches plus just a little bit. Okay. All right, let's change out. We're going to change out to our tap size now. Okay, 29/64 is our tap size. Same thing, we bring this in to where she just barely touches, and then we're just going to mark out. We're going to mark out on our ways here the same as we did before. Down here, we're going to give it another mark for about 1.5 inches there, thereabouts. We're going to be able to tell when we get down there the tone of the cut that we actually bottomed out, but we also like to have an eyeball of how far we are actually. Okay, I am going to slow this down just a little bit. I just don't want to burn out my bits before I get all 6 holes done. Like I said, this is tough stuff here. Still a little hard getting used to cranking the table in the opposite direction. I work I work in the head facing the other way so many times, more than I run it off this way here. About another ½ inch to go. I'm going to take some of them chips off. There we go. About 1/8 of an inch. Okay, I can hear a difference in the tone right there. Okay. Now we'll go ahead and pull that, and we're gonna chamfer that opening there before we tap. Just a tiny bit more. Okay, let's get set up for a tap. Okay, we went ahead and shut off our motor. We don't need to have that running while we're doing a tap because everything's going to be by hand. Put my tap follower in here. And I bought brand new taps because once you go through several of these holes, in fact, I bought one tap per shaft, so I keep these holes crisp. All right, and we get the tap started in there like that. Now, instead of the cotton oil, I'm going to use tapping fluid for the tap. And this is just, they call magic tap, but it is tapping fluid. And we get a good load on our tap follower. And there's not much room to swing a tap handle here, so I do use my crescent adjustable spanner. Well, have to go chase that down. Now this is a plug tap. It's pushing the thread down into the bottom of the bore, so the extra depth really helps out on that. I'm using my crescent in reverse direction. Normally you pull that way, but I'm just using it that way because it's more comfortable on my hand to go ahead and just hold the pressure to make sure that I'm not pushing that way on the tap more than I'm pulling this way here. I'm trying to pivot the tap, not put all the weight on one side. All right, we need to load this some more. Breaking taps is when you're trying to push the tap in another direction than it's intended to. It's intended to go straight down the bore, not off to the side. Nope, almost lost it again. Those little cans can fall into the T-nut slots very easy. Now we're taking this in to where we're just about the full depth of threads on our tap here, and then we'll back it out, and then we'll put a T-handle out there with it hanging in the air on the sawhorses outside, where we got room to swing the whole handle. But I need enough threads in there now to put that plate up there and tighten it up. Transfer punch the other 2 holes. Okay. Back this tap out, and this hole is completed for right now. Funny how much heat I got on the end of this thing. Of course, I could run my flood coolant, but the flood coolant would be running all over the place there, and I'd be like in Soupville here. And the thing about going in and out and drilling and trying to hold a coolant in on something that's moving in and out, a little more of a task than it is to put it on an item that's rotating, and that's why I'm using my sulfur-based cutting oil versus the other. Could have got one of my square sockets for this. All right, we'll get some air and blow that out. And our test bolt. All right. All right, we put our plate up here. We just put a nut on our bolt here so that we didn't have to use all the threads, but it locks it on. We took our dial calipers and we checked at 3 points like this, and we're within 5 thousandths. So we're content that we're center enough. This disc is got to be fairly close, but it has a little bit of play in on your threads as well. This is just a short transfer punch, and all I'm doing is putting this in here and giving myself a mark in here to zero in on to drill the other 2 holes. All right, and we have the 2 marks right there. Okay, we're going to put our tap follower in here, and we're going to bring the shaft in close, and we're going to rotate the shaft until it's in line with our center drill, and we may put the coax drill in here to verify that, and we'll rotate this while it's in the hang sky hook outside.